Okay, well, thanks everyone for coming and allowing me to speak about geophysics at a Geological Society meeting. So I hope I interest you enough. I will begin with a preface on the electromagnetic method for geophysics. It's not too much, so it's just a couple of slides, but So Richard Lane wrote this down as a functional form for what conductivity means in Earth systems. So conductivity is some function that is given to you by the pore fluid conductivities, degree of pore fluid saturation, the porosity of the groundwater, or the porosity of the material, the matrix that hosts the groundwater, a tortuosity function, which is a function of the pore size and the arrangement of the pores, and the conductivity of the solid matter that you measure. So when you fly an Airborne system, you are measuring some function that is a combination of these different variables. When you look at how does electromagnetic systems operate, how do they operate in geophysics, you have two fundamental laws to look at. The first one is Ampere's law, and the second one is Faraday's law. Ampere's law says that when you have a current, you create a magnetic field that rotates around that current, and that in turn creates an electric field that changes with respect to time. Faraday's law is the law of induction, which says that when you have a curl in the electric field, meaning that it changes spatially, then you create a magnetic field that changes with respect to time. And those two interact with each other and give you the electromagnetic signature of the Earth. The way you do this, and the way you achieve Earth measurements, is typically you have some sort of transmitter loop that is slung below an aircraft, like a helicopter, or slung around another aircraft, like a fixed wing. You send a pulse of current around that loop, and you have some receiver coils that are also on the frame or towed behind. So in the case of a helicopter system, you have a fixed frame with a transmitter loop and a fixed receiver coils. In the case of a towed bird system, you generally wrap the airplane around with coils, and you tow a bird behind you. And then you get exactly what I said before. Your current that travels around the transmitting loop creates a magnetic field, which penetrates down into the ground. It creates eddy currents because the ground has some sort of finite electrical conductivity, which means that when the magnetic field penetrates down, it is changing both with space and with time. Therefore, it creates an inductive coupling field that creates a closed loop of current, which is also changing with time, which means that it has to generate a secondary electromagnetic field. That secondary electromagnetic field then goes back into space, and you receive it at the receiver, and you measure the secondary field. From those things, knowing what the frame is, where it is, what the receiver coils are and where they are, and what the amount of current goes through that transmitter loop, and keeping track of your time from the signal measured in the receiver, you can predict the structure of the Earth in terms of its electrical conductivity. So that is basically the preface for electromagnetic systems. So when you look at it, this is always a slide that comes from Paleki, which says that if you look at conductivity of the Earth in Siemens per meter, or conversely the resistivity of the Earth, depending on which way you look at it, they're the reciprocals of one another, different Earth materials tend to fall within different bands of electrical conductivity. That gives you some indication when you fly a survey what sort of conductivities to expect, but also if you know what the lithology is that you expect, or you have a structure, something in your mind that you think, these are the things that I'm expected to see, then you have a sort of range of values that you can associate with those materials. And that's it for the preface. So the bulk of my talk will be about a variety of case histories that I've done over the past few years within Western Australia, focusing on Airborne for groundwater, for near-surface groundwater. These are generally run through state surveys, either the DPIRD or DWER. And they've engaged CSIRO through various mechanisms that have had me looking at the Airborne data and assisting with their interpretation, and ultimately looking at aquifer characterization, aquifer detection, groundwater conductivity, groundwater salinity, and where to drill. So we'll first begin up in the Gascoyne, which is a project that I finished quite a while ago now, which was for horticultural purposes. So it used to be the DAFWA, but now it's the DPIRD, Primary Industries and Resource Development, came to CSIRO and said, look, we want to drill upriver from the Gascoyne, upriver from Carnarvon. So horticulture has expanded in the past couple of decades, and it's expected to double in production value from when we did this back in 2012, 2013. And the current demand for water and the projected increase in demand for water was not going to be met by the existing network of bores. So they expected the demand in water to increase, and some of the bores that were down more towards the Indian Ocean, the DOW had reported that there was experiencing stress. Stress means is that they were mobilizing saline groundwater from the Indian Ocean, drawing it up into the aquifers. Once you've done that, your aquifer gets contaminated. It's very difficult to remediate the situation. So the solution there was to explore further upriver for more groundwater. DPRD came to us with the proviso that they were doing wildcat drilling. So they would go along the river, they would plow a path along the river, along the access channels and the existing reticulation network, further upriver, and they'd plug an exploration borehole down. They had a success rate doing that with 1 in 5. Every 5 exploration wells that they put down, they could convert 1 to production, which they thought was a pretty poor use of money. So they went and said, okay, well, let's fly an airborne survey. Carnarvon town is down here, and we just flew this little survey up the river about 40 Ks. I think these were 450-meter line spacings with a 150-meter line spacing in the river proper within the groundwater extraction zone. They wanted to increase their rate of success for conversion from exploration drilling to production wells to 1 in 3. That's what they came to us and said, can you do this? And we're like, well, maybe. I looked at this connectivity, the inverted data set for a long time, and I couldn't make heads or tail of it. And I've given this talk before on more detail, but basically what you have is you have the new alluvial aquifer, which, because this sits on a megafan from the old Gascoigne River, and then you have an old aquifer that sits underneath it, and then you have a calcareonite that sits underneath this, acts as an aquitard. And they are expecting both in-river and overbank infiltration of episodic cyclonic events that would recharge the groundwater aquifer, giving fresher water into the near surface. The problem with the system, the problem with the area is that it was so heterogeneous that you had some sort of gravel channels that would come in and out of existence, out of the river, main river channel back in, and then you also had depositional clays and sands. It was very hard to find a proper place to drill. So I just went back to the conductivity profiles and said, okay, well, let's just go back to the fundamental premise here, which is that below the groundwater table, where we have water sitting in the ground, we're going to posit that the conductivity, the bulk electrical conductivity that we obtain from the inversions, from the models, is related to the aquifer water quality. Therefore, I will seek out the lowest conductivities that I possibly can along the river. So if you take, say, an Airborne connectivity section and you draw it up on the line and you say, okay, well, where am I going to look here? We have the near surface. These are some of the clays and silts that are deposited in the very near surface. This is the Gascoigne River with a recharge zone. There's some clays and silts beneath it. And from borehole evidence, the water table sits pretty much beneath this conductivity bulge in the near surface. So the bottom of that layer approximately represents where the water table is. So that's my cutoff. I don't look at anything above that water table. And then I just look at where here can I find low conductivity values. And what's more, I say, starting from the water table layer, what directly beneath the water table satisfies some criteria that I set, say below 60 millisiemens per meter. And I pick out that layer. And then I go to the next layer down and I say, given that I've just passed underneath 60 millisiemens per meter, what beneath that also satisfies that condition? So you get something like this. You just keep going down. It guarantees that you'll have at best V-shaped formations in the conductivity profile, but these are all satisfying beneath 60 millisiemens per meter. And then I do it for 80, and I get something that looks like this from the near surface, and then I said, okay, let's go to 100, and I get something that looks like this. And then I calculated the thickness of each one of those from underneath the water table. And then I put them all together. And then I make this crazy map, which is just basically the reds are under 60 millisiemens per meter, the blues are under 80 millisiemens per meter, and the greens are under 100 millisiemens per meter from the water table down. The saturation of the color represents the thickness. So going back to my premise that airborne EM conductivity is a driver for groundwater salinity, or conversely, groundwater salinity tells me what the airborne EM conductivity is, I will seek out the thickest, lowest conductivity values along the river channel within this cyan boundary, which is the groundwater extraction zone. So then they said, okay, we want 70 drill targets because that's what our budget is. I'm like, 70, there's not that many targets. But what I'll do is I'll give you a priority listing of targets that I think are worthwhile drilling, starting from your reticulation network ending, which was somewhere around here, and going further along. So everything that was further away from the existing network, I downgraded in priority. And everything that was along here, where these things are thick and deep and low conductivity, I said, those are my priority ones. These are the places that you should go and drill first. And it turns out that if you did that, the priority targets one, there weren't very many targets that we had. There was some like 10 or 15. But we had a conversion rate from exploration drilling to production wells of 2 and 3. So every 3 holes that we put down, 2 of them were recommended to be converted to exploration holes. Every 3 exploration holes, 2 of them were recommended to be production. For the priority targets 2, it was about a half. And for the priority targets 3, which are further upriver, it was about 1 and 3. So even in our worst case, the ones that I thought were very marginal still got their expected success rate. Not only that, but they also offered some fairly significant pump rates for the Gascoyne River. Typically, they were looking at somewhere around 50 to 80 liters per second. I think it was something like that. So these were pretty good. What's more is that if you looked at the 2014, 2015 bores, which is ones that they drilled upon our suggestion in both the old alluvium and the new alluvium. I think we only picked the old alluvium for this because the new one is not really the area that you'd use for production. Then they went and drilled it. They did water sampling along the screened interval, and they found that the airborne EM conductivity was lower than where they picked them from the 2010 during the wildcat drilling. So the bulk electrical conductivity resulting from the inversions on the drill sites that they predicted with wildcat drilling and converted to production wells was in general higher electrical conductivity, not by much, but it was. And the groundwater that you pumped out, the salinity of the groundwater, or the electrical conductivity of the groundwater, was lower. So we got more low conductivity water in low conductivity areas. Furthermore, when you look at the distribution of lithology from the screened intervals, and you just do my dumb sort of categorization of sand and gravel, which are the aquifer ones that you want to produce from, and clay and sand and clay, which are the ones that are going to be marginal or non-productive, you intercepted far more of high hydraulic conductivity lithologies. So we not only targeted lower salinity groundwater, but we also targeted better productive aquifers, which I think was a pretty good success for something that I didn't think was going to work, given for the first few months that I was looking at the conductivity data. So that wraps up the Gascoigne River. Now we're going to go south of Perth down to Mile Up, which was an airborne EM survey commissioned by De Weur to look at groundwater in the near surface in the Mile Up region. Once they finished with the data set, they handed it over to DPRD, who was looking for groundwater for farmers in the region. And Richard George is the principal geoscientist at DPRD, so he rang me up and said, can you do some work with this airborne EM data set? I don't have much money, so what can you do with that? I said, okay, so what I'm going to do is I'm going to take the inverted products that came from the previous survey, and I'll try to work some magic on it. What do you want done? And he said, I want to look at the superficial aquifer, and I want to look at aquifers within the Leaderville Formation. And Phil, I think you've seen this, so forgive me if this is a repeat for you. So let's focus now on three main lines that I took from the inverted data. I can't remember the names of them. I think there's Binging Up, Harvey, and my own personal line, which I thought was really interesting. So Harvey and then Binging Up. So when you look at the available data that we had from the the stratigraphic wells that they put down, they had about 6 or 7 wells that penetrated through the superficial aquifer, which is that dashed line, down to the Leaderville aquifer, which is this other dashed line, and they generated the surfaces of those geologies for the region, and it was based upon those 6 wells. I looked at the inversions, thought I think we can do a little bit better than that. I'll take the information that I have, which is these sorts of pierce points that I have in the connectivity depth sections, and I will reinterpret these layers based upon the electrical connectivity that I see. So I reinterpreted the base of the Leaderville to be this line with some error attached to it, these solid lines. The superficial I didn't change. I didn't figure that it was worth putting in the extra time to remap the superficial because it's very near surface and it tends to be fairly flat. And then I went this one. Some of these lines represented a bit of a challenge. Like I would have perhaps picked something like this as the bottom of the Leaderville formation. It is still uncertain what this sort of connectivity increase is that wedges out. It could be part of the Leaderville formation that is more shaly or clay rich. It could be something like the Bassendean clay or Guildford clays coming down. I'm not a geologist, so I have no idea what I'm talking about sometimes with these things. I do know that there is a definite feature that comes across here that is related to the boreholes, that the algorithm that I used to pick this, I basically picked a bunch of training data and then it used the connectivity matrix in the surrounding neighborhood to re-predict this for me. And then you come right down to the south line, which is near Dunsborough, and you find this major dip in the Leaderville formation. And I didn't think at first that this was really real because I have no borehole evidence to prove it, either to prove it or otherwise. However, if you look at the nearby lines, north and south, something like this continues on, and it continues on and strengthens in its connectivity, and then it comes back up to surface. So then you take, so that's the sort of analysis that I did for that. Going back up to the near surface of the very superficial, the elevation of the superficial aquifer is based from limited drilling. The thickness of the aquifer gives you the volume, and then you include the water table. So that tells you where, in the superficial aquifer, where the water table is and where the base of the superficial is. That'll tell you the volume of the total contained aquifer. There were a number of boreholes that are in the registry that have measurement of the total dissolved solids across the area. Remember, this is it's a sort of a transient aquifer that people use when they can. So I used the electrical connectivity from the Airborne EM to give me some guidance in that. So if I look at the total dissolved solids on the logarithmic scale on the y-axis, and I look at the Airborne EM connectivity that is intercepted from the screen zone from those boreholes that we have, if I had that information, that they put down a pierce point, put down a borehole that they're using for production, and it's screened over a certain range within that superficial aquifer, I took the mean of the bulk electrical connectivity in that area, and then I fitted a sort of regression line against the total dissolved solids to the Airborne EM connectivity. Meaning that if I have this relation and I know the Airborne EM bulk conductivity, I can repredict what the expected groundwater salinity would be. It turns out that the errors on these give you about almost an order of magnitude variance in your predicted salinity, which is maybe not what you want, but it does kind of tell you where you should go for your near surface groundwater. For example, down here where that big dip was in the Leaderville, there's a couple of spots up here. Those farmers would probably be very happy. Anything over here is basically seawater penetration, so you don't want it. And up here, this is probably Tamala limestone that's coming through and giving you a low conductivity, but it's not necessarily a groundwater target. Okay, so let's go back to the Leaderville. So that kind of wrapped up what Richard expected from the near surface. It wasn't a great deal that I could do with that, given the paucity of borehole information. So as I said earlier, the base of the Leaderville is interpreted from a few bores in the neighborhood. And it's pretty much flat. It dips out to the west. So the thickness is also poorly determined because you don't know where any other members of the Cockleshell Gully Formation sits underneath it. So that was kind of the Leaderville, is from the superficial down to the contact with the Aniaba. So as I said, I went through the cross-sections of the Airborne, included the stratigraphic holes, and repredicted where the base of the Leaderville was. So I'll just go back. I was now looking for this contact. And I take that over the entire Airborne survey and I repredict the elevation. So from that, I get something like this, where the green and blues represent a lower elevation, therefore a deeper base of the Leaderville aquifer. This is the line that I was talking about, where there's something very deep going on that goes south. There's a ridge here, which I think has been alluded to in the literature, although I thought it was perhaps up here from the literature. But then up here in the main part of the Airborne survey, it's a fairly deep part of the Leaderville aquifer. So we remapped the base of it based upon the Airborne connectivity. Having said that, I don't know whether it's correct. I have gone back to Richard George, and he has drilled a couple of sites along here, and he has got back the results that we'd expected, that if we drill here, you should get something like 180 meters of fairly good groundwater at depth, and you shouldn't be intercepting the Aniaba Formation until like 200 meters or something. And he came back saying, yeah, 2 out of 3 ain't bad. He put 3 boreholes down. He told me about 2 of them. I haven't heard about the last one. We sought advice from Dewar about whether this is an improved base of Leaderville, and anecdotally I heard that they said that, yeah, it's good, but I don't have any evidence from new drilling. So yeah, I've got the thickness. So the thickness, I've estimated that I've increased the volume by about 4.5%, which is about 3,600 gigaliters. The total volume is somewhere around 83,000 gigaliters of volume. If you can estimate the porosity, then you can get your available groundwater that would be in the area. And then we go, where are we going to drill? So these are the targets for the potential area. These are the thickest areas of the Leaderville aquifer. There was some borehole evidence of what the quality of groundwater was from production wells, licensee bores, and monitoring bores. For some reason, you don't have any licensee wells that have high groundwater salinity. So they only want to report the things that they're producing groundwater from. So I do the same thing and I predict, well, what is my best prediction from bulk conductivity to groundwater quality? And went from there. So then you ask, well, where do I drill? So now I'm doing the same thing that I did in the Gascoyne. I choose an Airborne derived conductivity, some sort of threshold, say lower than 40 millisiemens per meter, which is probably good groundwater quality. Then I contour out the thicknesses of it. So darker blues are thicker aquifers. Then I combined that with the depth to the top of that volume. So I found these volumes of low conductivity somewhere in the ground. And this red one is just a map of how deep is it. And I think I reversed the colors so that the darkest reds are the nearest surface. So I want to look for dark blues and dark reds because they are thick and near surface. And then I combine those color maps and I'm looking for deep purple. And then I said to Richard, this is where you should go from here, and this is where you should go down here. I'd recommend drilling there. He said, that's out of my region of interest. I'm just interested in the north. And that's where he put down the holes, and that's where he got good results. So happy with that one. Okay, well now we'll move up to the north to the Murchison, which is another crazy problem that we had. Department of Water came to us and said, we want to map out palaeovalleys in the Murchison. I know that other agencies have done this in the past, but they came back and said, we want to find these groundwater reserves in the paleo channels. How can you do it? We've got $1.5 million to fly. Like, okay, how big is the region? They said, oh, it's about 300 by 400 kilometers. Now, if you know about planning Airborne surveys, that's not going to get you very far unless you do very wide line spacing. So they still wanted something that was a tight line spacing, say 4 to 5 kilometers. So we're like, okay, well, we can attempt to do something like this. Now, the reason is they just wanted more groundwater. So they know that there is groundwater resources within the paleochannel complex. It's just we don't know where it is and we don't know what it's like. So what can you give us? And I'm just going to focus on one thing, which is where is it? So this was, at its time, one of the largest surveys in Australia. It took up, in total survey area, it took up 6% of the Western Australia, but it doesn't actually fly in a grid that like you'd understand normally. So we began with the Mr. VBF, which is the Multi-Reflection Valley Bottom Flatness Index, which is something that CSIRO and Geoscience Australia produced, which says that it's kind of like a combination of elevation and spectral data that says these are the regions which are the flattest. So we said, okay, well, let's posit that the paleochannels that are existing are underneath contemporary valleys. So we planned the Airborne survey based upon a certain index of the MRVBF. And then we asked various contractors to go and fly this. And they weren't too pleased. And the reason is because it's a mongrel of a survey to plan. We had 3 different survey regions, and I will be focusing mostly on the northern region because that's where the results are best. Then we had this central paleo-valley system, and then we had the southern, which was much more marginal in terms of its in terms of where it was. And these are now 4K line spacings. And it would be very interesting to get some of this other data if you were a minerals explorer, because what they would have done was they would have flown these entire lines from start to finish on these given directions. But we only purchased the parts that were inside here. So they have the data, they just haven't sold it to us. Now, whether they're doing something with it themselves remains to be seen. So let's just take an Airborne cross-section where we had some boreholes. Again, there wasn't very many boreholes in this area. And you can see where the groundwater table is sitting in here. You could see where the palaeovalleys are incised in the craton. And then you can also see that there are some things that are infilling these paleochannels. Now, our interpretation is that in some of these regions you have a calcrete, there's a water table that exists, which I already mentioned. In other parts of the paleochannels, you will have some sort of combinations of clays and sand, and then hopefully over top of that, more sandy regions and other areas that are offering some sort of recharge or groundwater potential. You don't necessarily want to go into these regions. I can't recall at the moment how conductive these were, or even whether the drill hole information told us what these materials were, but they were generally expected to be poorly productive for groundwater exploration or groundwater extraction. So maybe you would look for the areas up here, or maybe on this paleochannel over here. So what I did for this, to give them an idea of what the paleovalley structure looks like, which is what I'm going to talk to you about today, I went and picked every single one of those lines, the base of the paleochannels in the region. And then I came out with some sort of paleochannel depth map, which is what you see here. Now, it's not perfectly right. I know, I'm aware of that. It's probably not even reasonable in some areas, but I know that in certain areas, like in the northern channels, this is pretty good. And the colors go from, say, 0 or 5 meters in the lightest or the darkest blues to something like 150 to 200 meters in the deepest reds. And you can see this paleochannel. I can't detect underneath this because there was a salt lake here, but the paleochannel kind of goes up to the north, curves around. There's another tributary that comes along, it curls around and comes out and goes down into the SKA array. And from that, we said, okay, there's your total volume of the paleochannel that you can get. Interestingly, when you ask, did we miss any paleochannels by not flying the places that weren't flat? The answer is that in some cases, yes, we probably missed a couple of places that we didn't get the termination of a paleochannel or the genesis or the beginning of a paleochannel. And in some cases where the lines were very short and still far apart. Remember, this is a 4-kilometer line spacing, and I'm gridding at 1-kilometer cells. And my structure, my geological structure, is not perpendicular to the flight lines, which makes a nightmare when you're gridding. So I had to spend a long time redeveloping an anisotropic gridding scheme to make these things look much better. Otherwise, you have these boudinage effects, which is just beating, beating, beating. You can pick along a line, yeah, there's a deep paleo channel, but when it comes to the interpolation to the next line over, it just goes up to the near surface and comes back down again. So I improved that gridding in some areas, but in some areas, it just doesn't work that well. Our advice to the department was, this is not a groundwater exploration map. This is a groundwater potential for exploration map. What you have to do is go on and say, oh, this looks interesting. This is nice and deep. Let's follow up with some more geophysics or some drilling. They released it to the public, and then they got some angry calls from some farmers who said, I drilled something on your map and I got rock. Like, yeah, well, we did say that you shouldn't do that. This is a map, a product that tells you where you should keep looking. It's not the end product. 4K line spacing, unless you are planning to drill exactly on that flight line and you're looking at the cross-sectional data, I wouldn't advise drilling anywhere. However, if you're on the line, then yeah, go for it. Okay, so that was the Murchison. Now we're going to move up to Newman and another DPRD project that we're still working on at the moment. And this is a can of worms. So this is for a managed aquifer recharge in the Pilbara. You know, you've got Newman down here. You've got various mining efforts around here and over here. What they did was, this is a royalties for region, which is where a lot of the funding comes for groundwater projects that at least I'm involved with through the government agencies. And they wanted to find suitable sites for managed aquifer recharge. Or, if you can't find any, where are the groundwater reserves to be found? Is there available groundwater that we don't have to build a groundwater mountain for? And basically they want to use this region, which is sort of the Fortescue Fan region and manganese group, sort of flat. They wanted to use it to increase agricultural production. And they wanted to improve their understanding of the wet Newman formation. Now, there's a lot of history in this area, and there's some weird things that go on. Ophthalmia Dam is down here. It's a dam for the workings from BHP. They know that it leaks, which is fine. I mean, that just happens. Rio Tinto's empties stuff out into the Ethel Gorge, which comes up and goes somewhere. That was the advice that we have, that it goes somewhere. However, from the drilling that there is existing in this area, they've noticed that over the past 15 to 20 years, the groundwater table is increasing. So the water is going somewhere, but then it's not really going somewhere. It's going up, they know that, but then they're not really sure where it goes. There is a major driver of groundwater, which is called the Poonda Fault, which cuts between the Bulgita Iron Formation to the manganese group and the Whitnum Formation. And something really curious is going on. So I'm going to show you a couple of Airborne not flight lines. The flight lines are this way. I'm going to show you some cross-sections from the Airborne gridded data to draw your attention to the fundamental problems that I'm facing right now. I may have missed a slide here, but let's start in the northwest corner. I'm pretty sure I did miss a slide here, but I can't go back because we're recording. So I'll just see where I get. This is the short cross-section of what's happening up in the northwest corner of the Airborne survey. So the Airborne results giving you some sort of conductor that goes down to, say, 100, 150 meters or something like that. 100 meters over here is maybe 120. And there are 3 or 4 different features that I can see from the Airborne. The first one is that the groundwater table probably exists somewhere here. That would be at least my basic interpretation, given the evidence that I've had in the past from looking at Airborne. Then there's some sort of bulk conductor, which I would guess would be some sort of transported detritus. So that's probably part of the transported layer of the Fortescue Fan, for example. Then there seems to be a lower conductivity wedge that comes in and out of this region. Over here I have the Whitnum Formation, and over here I have the Bulgita Iron Formation. And then there is a base layer, which I am guessing is probably in situ weathered Whitnum Formation. It's higher in conductivity, not by much. So my estimation was the be that it consists of heavier clays, silts, less gravel, less productive for groundwater. But there is a really nice feature right here, which is a low conductivity wedge that comes out that exists across multiple flight lines. So I said, this is one of my primary targets. I know it's not near Newman. I know it's a little bit hard to get to because there's not many access roads. But if I was going to drill, I would drill here to answer a few questions. I'd also put one here, but it depends on how much money you have to spend. The questions that I would like to answer by a drill hole like this is this actually the water table? Is this actually a low conductivity sand or gravel lens that exists that's transported cover, so high energy transport from the hillside nearby? And if so, does it contain good quality groundwater? And then finally is this a transported or in situ weathering formation, and is this the boundary between that formation and the Whitnum proper? Those would be my questions to ask. They're going to drill this in the next few months, so that's looking at that. If you go back, if you look at that interface where I had the Whitnum formation and you go and map out the entire area, then you can get a thickness of cover map for the entire area. And this is the Whitnum formation. It tends to be highly thick cover. Where I was looking at was just over here, which is a thick cover sequence. This is the Bulgita Iron Formation. This is the GS WA map of where the Poonda Fault is. Then it jags and then continues down and jags and continues down. This is their map of where the Fortescue River Fault is. Now, I dispute those results based upon the Airborne conductivity, my cover map, which is basically based upon differences in electrical conductivity from the near surface down to the bedrock formations. And that's what I'm trying to find. I would put the Poonda Formation a little bit further south. I would put the Dogleg a little bit further to the northwest. And then I'm not sure what I'd do here. And then it would come down south, jags down, jags up again, and comes across, jags down, and kind of goes around. This is another one that BHP expressed interest in. There is a paleo channel that comes off here, and we presume that it could have caused some sort of weathering formation here when it was higher energy. You can see that there is a paleo channel from the Fortescue River that sits kind of underneath contemporary drainage, which is what you'd expect. And I think that the Fortescue River Fault is actually kind of more here or here, that's the interface between a schist formation. Is it? I can't remember what it is. This is the manganese, and I had it on the tip of my tongue, and the Whitnum Formation. And I think the Whitnum Formation probably goes here more, unless there's something else going on in terms of what the weathering patterns were. So that's where we're sitting. These blank areas are bedrock highs. I didn't bother interpreting them because the low conductivity was very near surface, and I couldn't tell the difference between whether it was low conductivity due to bedrock or low conductivity due to unsaturated materials. So I excised those from my interpretation, all of these little regions, which kind of maps sort of well with the regolith maps that say that these are exposed, what they would classify as exposed regolith. So if I was to drill for groundwater resources, I'd put it somewhere along here, somewhere in there, perhaps, maybe up along here. And who knows what's going on? Look for the middle layer. Okay. Oh, so that middle layer, I've stepped through too many slides and I did miss a slide, so I'll try to recover myself here. That middle low conductivity layer, I interpreted across the entire survey, and then I grid out what its thickness is in the entire survey. So I've said this middle aquifer layer, which I've just called, I think, middle alluvial or middle aquifer, I'm saying that's probably an aquifer, I'm not sure, but if it was, how thick is it over the region? Because I know that it's low conductivity, and I know from experience that low conductivity in these sorts of settings is going to tell me that there's generally good quality groundwater. So then I produced this map of what is the thickness of that middle layer. And then you get this sort of map, which shows you where the paleo channel has emptied out. It kind of goes out to the north. There's a couple of things that are in the Fortescue fan, which is this sort of structure here to here. There's something happening in the northwest corner of the survey. There's something happening in the southwest corner of the Whitnum Formation, which butts onto the Fortescue River Fault. And I would drill there and there if I wanted to drill close to Newman. Otherwise, I'd go down to this region in the manganese group, or perhaps further along down to these regions, and hope. Again, this is not going to tell you what those materials are. It's going to tell you these are the places that I would go if I was going to drill. And I wish I had those other slides for you to show you the problem that I had with the Ophthalmia Dam, because from the borehole logs that are drilled in the 70s that have poor information about where their screening interval is, and from the Airborne EM connectivity, the Airborne EM connectivity is much like you saw on the slide, which had a near-surface low conductivity profile that was fairly horizontal related to the elevation. Beneath that you had a high conductivity bulge, which I suspect is transported sediments that are like clays and silts. And then beneath that again you had a low conductivity feature, which I thought was probably sands and gravels. And the water table pretty much followed elevation, at least as far as I thought. But when you looked at the borehole information, the borehole groundwater table was sitting at about 10 meters, 10 meters, 10 meters, that seemed to fit my interpretation fairly well. But then as soon as you got near the Poonda fault, the groundwater table drops down to about 35 meters. So there's a question there is, are the bores too old? Do I have proper information about the screening interval for those bores? Is that the water that they're measuring, the elevation of that water that they're measuring, is that from a lower aquifer that is not under pressure, so it's not bringing a water table closer to the surface? Or am I completely wrong in my interpretation of where the groundwater table is? They're going to re-drill some of those holes, so it remains to be seen. I apologize that I don't have that slide. I don't know what happened. So here are some of my key highlights in my search for groundwater in WA. In the Gascoyne, we improved target detection to a 2 and 3 in best case, 2 and 3 conversion from exploration wells or exploration bores to production wells. And then we found better quality groundwater from more productive locations. So that's a bit of a win. In Mile Up, we looked at salinity maps for the superficial and, in Leaderville aquifers. And in my view, we improved the interpretation of the lower boundary of the Leaderville formation. However, that's a qualified improvement because it's still reliant upon sufficient drill hole information. And whatever was happening down in the south, I would love to see that drilled because that looked fairly deep and fairly low conductivity, and just be great to see what's going on down there. For the Murchison, we produced a paleo channel map, and we made an attempt at getting a groundwater quality map for that network based upon the available boreholes. But this is a 400 by 400 kilometer region, and we had maybe 25 to 30 boreholes in that area. So a groundwater salinity map for something that large over that extensive an area, I would hesitate to call a good product. That would rely upon further drilling and further exploration. And in the Newman, I wouldn't call it a highlight. I've opened up a can of worms with this project. There's definitely some areas that could be used for managed aquifer recharge if our interpretation is correct, that if you have a fairly thick superficial that's low conductivity and you have a good thick base of high conductivity, which is probably clay, you could potentially build a groundwater mound. However, I think there is fairly good reason to believe that there is a fairly extensive low conductivity groundwater reserve already present, negating the need to build a groundwater mound. That's going to be determined in the next, I think, year to year and a half. So we'll see about that. So for most of my work with CSIRO, I have focused on Airborne EM inversion and Airborne EM modeling. And I would say that Airborne EM has moved from minerals detection. This is not a brand new statement. I mean, Airborne EM has moved away from minerals detection as a primary method of choice for a long time, at least 20 years. And it's just that it's nice to see when you have these large projects like you have in Australia, where you have very big regions where you don't have a lot of information, to use something like this, which is fairly cost effective and fairly cheap compared to drilling. I mean, imagine drilling the Murchison Paleo-valley system at 400 by 400 kilometers. That would just be crazy. Cost of $1.5 million for an Airborne EM survey to give you that much information. It's pretty good value. And I routinely use this in groundwater exploration and near-surface exploration. And I think that sums it up. So thank you very much for your time. I hope it was interesting.